Dear conference participants, the travel and salesman problem asks the following questions. Given a list of cities and the distance between each pair of cities, what is the shortest possible route what visits each city exactly once and returns to the origin city? It is an NP-hard problem in combinatorial optimization, important in theoretical computer science and operation research. The travel and salesman problem occupies a special place in combinatorial optimization and operation research. Historically, it was one of the tasks what gave impetus to the development of these areas. The simplicity of formulation, finiteness of the set of admissible solutions, clarity, and at the same time colossal cost for a complete search still push mathematicians to develop new numerical methods. All new ideas are first tested on this task. The most important generalization of the travel and salesman problem for transport and logistics what several vehicles with limited capacity must serve customers by visiting them in the specified time windows. The ideas of the local search were developed in metaheuristic in general schemes for constructing algorithms what can be applied to almost any discrete optimization problem. These are general iterative processes what use randomization and the elements of self-learning, search intensification and diversification, adaptive control mechanism, constructive heuristic and local search methods. Metaheuristic include genetic algorithm, evolutionary computation, taboo search, simulated annealing, greedy randomized adaptive search procedure, ant colony optimization, and others. Metaheuristic are divided into trajectory methods, where each iteration has one valid solution and the transition to the next, and methods what work with a family population of solutions. The first group includes taboo search, simulated annealing, and other. Trajectory methods live in the search space a trajectory, a sequence of solutions where each solution is adjacent to the previous one, concerning some neighborhood. The second group of methods includes genetic algorithms, evolutionary computation, and ant colony optimization. At each iteration of these methods, a new solution of the problem is built, which is based not on one but several solutions of the population. Attempts to spy out of the methods of solving difficult combinatorial problems in nature are finding a new incarnation in numerical methods. Artificial intelligence researcher Marco Dorigo described in 1993 a method of heuristically generating good solutions to the TSP using a simulation of an ant colony called ant colony system. It models behavior observed in rural ants to find short path between food sources and their nest, and emergent behavior resulting from each ant's preference to follow trail pheromones deposited by other ants. Ant colony system sent out a large number of virtual ant agents to explore many possible routes on the map. Each ant probabilistically chooses the next city to visit based on a heuristic combining to the distance to the city and the amount of virtual pheromone deposited in the edge to the city. The ants explore depositing pheromone on each edge what they cross until they have all completed a tour. At this point, the ant which completed the shortest tour deposits virtual pheromone along its complete tour route. The amount of pheromone deposited is inversely proportional to the tour length. The shorter the tour, the more it deposits. In our time, the travel salesman problem, TSP 3D variation, has gained new application. For example, in the process of 3D printing, there is a need to minimize the transitions of the printhead from the endpoint of the path to the starting point, which reduce the deteriorating print quality. The problem of unmet aerial vehicle trajectory optimization is also related to the two existing common classic tasks, the salesman and the transport problem. The problem of three-dimensional UAV path planning areas when it is necessary to plan traffic in mountain conditions or a multi-story urban development. With the increasing complexity in indoor living environments, there is a growing need to optimize indoor navigation. Thus, we can see the widespread use of ant colony optimization in various fields, which indicates its effectiveness and versatility. As mentioned above, if the vertices of the graph are points of the plane with coordinates x and y, and when in the main matrix traveling salesman problem, the elements of the matrix are determined by the formula of the Euclidean metric. For the salesman's spatial problem, the distance matrix will be determined by the formula on the slide. We propose the use of the ant colony optimization algorithm to solve the spatial problem of salesman 3D variation of TSP. The ant colony method can be applied to any combinatorial problem that can be consistent with the following requirement: appropriate representation of the problem. The solution space should be represented as a graph with a set of vertices and edge between the vertices. A correspondence must be established between the solution of the combinatorial problem and the root in the graph. It is necessary to develop rules methods on the slide. An important rule in AND algorithm is played by the probability proportional rule, which determines the probability of transition of the k and from cti to ctj on the t iteration. The choice of the city is based on the principle of the roulette wheel. Each city has its sector with an area that is proportional to the probability. There are three variants of the AND system algorithm which differ in the method of calculation delta tau sub IGKT. In the first variant of the AND cycle algorithm, after the completion of the root, each AND k deposits the amount of the pheromone on the rib. To study the entire solution space, it is necessary to ensure the evaporation of the pheromone, a reduction in the amount of the pheromone that was deposited in the previous iteration. Let us denote the evaporation coefficient of the pheromone by p element 0, 1. Then the pheromone update rule will take shape, shown in the slide. You can see the flow chart of AND colony optimization algorithm on the slide. The program code is implemented in MATLAB. During computational experiments, various network topologies were randomly generated, and the number of iterations at which the optimal cycle was achieved was recorded. After the development of the AND colony algorithm to solve the spatial traveling salesman problem, computational experiments were conducted to compare the computing resource needed to solve the 2D and 3D traveling salesman problem. The number of vertices of the graph varied in the experiments. During random experiments, different network topologies were generated, and the number of iterations at which the optimal cycle was achieved was recorded. Table shows the dependence of the time to find the optimal route on the exam to randomly generated test graphs with the number of iteration 500. The execution time of the code for the TSP 3D task is almost the same as the execution time of TSP 2D on the slide, showing the same proportional dependence of groove after reaching the number of vertices 100. Visualization of the best rounds was carried out using the function plot and plot free. It is worth noting what visualization consumed most of the computing resources. Analysis by profiler showed what 71.4% used graphing function for 2D and 73.1% for 3D task on average. The results showed what the execution of the code for the TSP 3D task is almost no different from the execution time of TSP 2D. The results can be used for special tasks on the salesman TSP 3D variation, which arise in the process of 3D printing, planning, UAV trajectories in mountain conditional multi-story urban development, road planning in multi-story buildings. Thank you for your attention.